Before we talk about the Mandelbrot set itself, let's establish a few key concepts. Firstly, let's define imaginary numbers. The imaginary unit, I, is defined by I is equal to the square root of -1. Here are some properties of it. Multiplying two imaginary numbers produces a real one with an inverted sign. Next, there are complex numbers. These are numbers that have both a real and an imaginary component, written in the form of a plus bi. Doing operations with complex numbers is not difficult, just tedious. Because these numbers have two components and cannot be represented as one value, we use a graph instead of a number line. This is called the complex plane, and any point on here can represent one complex number. Instead of our typical axes of x and y, we have the axes of real and imaginary. This is the equation that defines the Mandelbrot set. C is a point on the complex plane, and the result of this equation will tell us whether or not said point is in the set or not. First, we assume z to be 0 and solve. Then we take the evaluated value and substitute it as z, running the equation again and keeping c the same. This process is repeated or iterated as long as computationally possible. If this equation ever results in a number greater than or equal to a specified radius from 0 plus 0i, it is not in the set. For the Mandelbrot set, this radius is 2. You can see that any final value that falls within this circle is in the set, and anything outside it is not. In this equation, however, z and c are complex numbers. This is what creates difficulty and confusion in the realm of programming the set. There are two ways in which we can turn this concept into code. The first is to create a class for complex numbers, one that will allow us to perform operations with them with ease. This is possible, but requires a lot of manual coding that doesn't make a lot of sense. The other way in which we can do this is to represent our complex number-based equation in two equations, one for real and one for imaginary. The way that this is done is by writing out our equation, z squared plus c, with actual complex numbers. The goal here is to separate this equation into its real and imaginary components, which means we have to do some simple algebra here. This results in the following equation, which can be separated into real and imaginary functions. Here's some pseudocode that makes use of these equations. Let's run through it. We start by creating double arrays for both the z and c. These will each hold two values, one for real and one for imaginary. Next, we declare iterations, which we use to keep track of how many times we have iterated this code. Next, we declare max iterations, which determines how many times our equation will run before we assess whether a point is in the set or not. As this value increases, so does the accuracy of the fractal and the length of the execution time. We then begin a loop for each pixel on the screen, each of which representing a point on the complex plane. Most languages simply won't order x and y the way we want them, so it's important we translate 0, 0 to the center of the screen. Now, we set c to be the x and y of the current pixel, z to be 0, and the iterations performed to be 0. Now, execute the following code while we haven't exceeded our limit of iterations. Compute real and imaginary values of z, check whether or not we have exceeded our radius, 2, and break out of the loop if so. Increase iteration counter. Once the loop has finished, we check whether or not we have used every iteration and still do not escape. These points that have not escaped will be considered inside the Mandelbrot set. Those that do not meet this condition are not in the set. We can color this with simple black and white to create this image. I hope you enjoyed this video. If you did, let me know. Thanks for watching.